The first one here is just some definitions. Let's talk through them, make sure we understand some of the differences, such as detection limit versus reporting limit, internal standard versus standard addition, these kind of things. We can even come up or write out the formulas that would be appropriate for those type of problems. Okay. So what's the detection limit?
How far something measures, I guess? Lowest amount.
Okay. So lowest amount that can be measured, but we can be a little more formal in the definition and say that it's the smallest amount or smallest quantity that can be distinguished as being significantly different than 0. So we could say be measured. As being significantly different than 0, or the blank. Okay, if you ran a blank sample in your mix. Does that make sense? Okay.
Dr. Kinney, it's not really quite getting, it's kind of blurry on the words and stuff. It's not really making them out.
Well,
I
don't know that there's too much we're going to do about getting the words, but I think at least getting the verbal explanation will be helpful. So.
Just checking.
All right, how about the next one, sensitivity? How sensitive something is, okay, yeah. So let's put it in terms of making measurements. No, not how precise. Okay, well, let's take if we took somebody who we would say is sensitive, right? They watch that tearjerker movie and they respond to what they see on the screen, right? Well, when we're talking about making chemical measurements, we're looking at basically how responsive the particular method or instrumentation is. And so we can, again, be fairly specific and say that the ability of a method to respond to a change in concentration. Okay?
Does it have to be concentration?
No, well, to respond to changes in chemical property or analyte quantity. I mean, that's so the ability to respond measurably to a change, we'll just say a change in analyte. Because you can think about this as if you had two different methods and you took two samples going into each of those methods and one was 0.5 ppm and the next sample is 0.6. Within experimental error, some methods, those may essentially look the same to each other. And you're not going to see a substantially different response in your method. In another method, you might see a clear response. Well, the one that you see that clear response is going to be more sensitive. We also talked about this with respect to calibration, right? If we're looking at a calibration curve, and we have one that looks like this and one that looks like that, where this is going to be our instrument response on our y-axis, and we'll say concentration on our x-axis, we would be able to say that, well, whichever method is represented by this upper curve here is more sensitive because it's got a larger slope. You get a larger instrument response for a smaller change in concentration, right? Make sense? specificity is our next one there.
Specific your response is?
Okay.
Or how? What specific changes?
Well, okay, so when we talk about specificity, we're talking about the ability to distinguish one thing from another, and usually we would state that with respect to the matrix. So, ability of a method to distinguish the analyte from the matrix, or everything else in your sample. Okay? All right. How about reporting limit? Ideas on reporting limit? And we can reference our detection limit here, okay? Reporting limit is going to be a value that's higher than our detection limit, okay? Usually it happens to be about 2 to 5 times, somewhat of an arbitrary decision made, but 2 to 10 times the detection limit. And really what this is now we're not talking about just being able to distinguish it from 0, but we're talking about the ability to have confidence in the value that we're reporting. So we're going to say a concentration below which there is diminished confidence in the accuracy of the result.
Does that include 6th grades and stuff?
Well, what do you mean?
You know how you have to, when you're reading a graduated cylinder, you have to sort of go off that last number and sort of get that last number, that kind of thing?
No. This is, we're saying, again, we're talking accuracy. So it's one thing to be able to say that something's there. Okay? It's another thing to say that something's there and how much of it there is. So when we get down pushing towards the detection limit, we might be able to say, yes, it's there, but we're not very confident that that 1 part per million number is really accurate. So we're going to set this as 10 times the detection limit, and below that concentration, we might say it's there, it's detected, but we're not going to quantify it. And that's pretty common that will happen. Did you have a question, Jim?
Well, I was just thinking kind of like, what was it, 3 times the baseline, or was it?
Yeah, so sometimes detection limit would actually be defined as 3 times the baseline. Again, being able to distinguish it from the baseline, that is a definition that you will come across. Okay. All right, matrix effect. So we're going to have some effect by everything that's in our sample, or something that's in our sample other than the analyte, and that effect is going to interfere with the response. Okay? So we could say change in analytical response as a result of something in the sample other than the analyte. And it's important to recognize that that could be both a positive and a negative, or a negative effect. So you can have something in your sample that may enhance your response. You may have something that may decrease it or limit it. Okay. How about internal standard?
A known value added to the known value of analyte added to the solution.
Okay.
Or
Well, it's certainly going to be a known amount of something. Except it wouldn't be accurate to call it analyte, because when we use an internal standard, we're adding something specifically other than our analyte to our solution. So we might say of a known amount of standard, and it must be something that is not present in our sample. How do we utilize an internal standard? Why even bother adding it?
matrix effects.
Okay, it's to overcome matrix effects. So we are assuming that any effect that occurs on an internal standard as a result of the matrix, so we say any effect on our internal standard by the matrix is proportionately the same or relatively the same on the analyte. So in other words, if we run our internal standard in our set of calibration standards, okay, and then we add our internal standard to our sample that has our unknown quantity of analyte, and we see a 10% decrease in the response to our internal standard in our sample, then we are assuming that there is also going to be a 10% decrease in the response to our analyte. Okay? You guys remember how we set that up? Formula that we use? We looked at our instrument response to whatever our analyte is, X, divided by the concentration of X. Okay? So we're looking at a ratio of our instrument response to our analyte and the concentration of our analyte. That's going to be equal by some factor, response factor, F there, to the instrument response to our internal standard divided by the concentration of our internal standard. Okay? So we establish what that response is. And that's just to take into account that an instrument isn't going to necessarily respond equally to two different substances. Okay? Usually we forego taking this approach and we actually incorporate it into a full calibration, where that calibration curve now looks, we still have concentration of our analyte as the x-axis, but on the y-axis we're going to look at the ratio, the instrument response to our analyte divided by the instrument response to our internal standard. Okay? And you still are looking at calibration curve just like you would in the absence of an internal standard. Okay? It's just that in order to come up with concentration, there's two values that you're putting in there. And you're looking at that ratio. All right, last one here. Standard addition. Exactly. Okay. Say a known quantity of standard analyte. And we're going to look at how does the instrument response change in response to this known quantity added. Again, we are trying to overcome matrix effects. Okay? And if we look at mathematically how did we describe that, for a single standard addition, we are looking at, okay, well, the concentration, initial concentration of our analyte X divided by the final concentration of analyte X plus the final concentration of the standard that we added. We're going to look at that ratio and say, okay, well, that's going to be equal to a ratio of the instrument response to just X divided by instrument response to S plus X, our standard analyte that we added, plus the analyte that we started with, right? We're just simply looking at a ratio. Keeping in mind, to get to the final values here, all we're using are dilution factors, right? You guys recall that? Okay, any questions before we move on? All right. I would like us to determine what the concentration of aluminum 3 plus is, expressed in parts per million, in a 250 milliliter saturated solution of aluminum hydroxide. We're given the molecular weight of aluminum hydroxide as well as the KSP for aluminum hydroxide. We are told that we can assume that the density of our aqueous solution is 1 gram per mil.
Where do you find the mole of aluminum hydroxide in the solution? But then you have to use like KSP from that kind of aluminum?
Okay, well, let's start with that notion of KHP, all right? So we have some aluminum hydroxide. We put enough of it in water so that we end up with a saturated solution, okay? That means that we are going to reach equilibrium with our aluminum hydroxide solid and aluminum 3 plus and hydroxide in solution, right? And that is our KSP. KSP is 3 times 10 to the negative 34th, right? And that's going to be equal to concentration of our aluminum 3 plus times concentration of our hydroxide cubed, right? Okay, so we need some values to plug in here. Okay. This is a solid, doesn't show up in our equilibrium expression, our KSP expression, so we're not really concerned with our aluminum hydroxide here, right? Over here we're going to say, well, we start with 0 of each of these there, okay? Now we need to assign some variables. What do we want to assign as a variable for our aluminum and our hydroxide? I like X and 3X. I think that makes sense for us. So we can come over here, say that we have X times 3X cubed, right? So we can simplify the right side. If we cube this, what do we have? All right. And then give me an intermediate step here. We divide by our 27 here. We just got a calculator. And can somebody complete this for me? The 4th root. that's going to be concentration, right? Okay. I had an error in my calculation, so I'm going to need some help here. All right, so this is in molarity. Okay. We have to get to parts per million. Now we do need to know how many moles then of material we have, right? Okay. So if this is the concentration of our aluminum hydroxide, we have, of our aluminum, we have a volume, 250 milliliters, or 0.250 liters. Okay. Times our concentration, 1.8 times 10 to the negative 8 moles per liter. Okay. That's going to get us into moles of aluminum. But then we have to get to grams, correct? All right. Somebody carry that out for me. All right. 1.2 times 10 to the negative 8 grams of aluminum 3 plus. Then what?
Convert our milliliters of solution to grams of solution.
Okay, and that would be 250, right? Because we're assuming density 1. 1.2 times 10 to the negative 8 grams divided by 250 grams times 10 to the 6 to get it in parts per million, right? And one final step here, if we get some help there.
.9
10 to the minus fifth parts per million. All right. Any questions there? No? Not yet, okay. Well, let's go back to our acids and bases here, and particularly with our weak acids and weak bases. I want to know what is the pH of the solution prepared by dissolving, there we go, by dissolving 0.25 moles of sodium acetate. We're told that the conjugate acid of our acetate, acetic acid, has a Ka of 1.75 times 10 to the negative fifth. We're dissolving that in water so that we have a final volume of 500 milliliters, i.e. we put it into a 500 ml volumetric glass. We'll answer that before we move on to the next part there. Okay? What do we need to do to solve this? So we're looking for pH, right? What's going to drive the pH of the solution? The acetate, right, that we put into solution. Okay, so we're putting some, oops. Putting some acetate into solution. It's going to react with water. We are going to end up with some acetic acid and some hydroxide. And it's that hydroxide that we need to get in terms of the concentration in order to determine pH. Okay. So we'll set up a reaction table. What kind of reaction is this? How would we classify that? KB, right? Okay. Well, we know how many moles. We have 0.25 moles. We know the volume, 500 mils. So we can determine concentration. It's going to be 0.5 molar, right? Not really interested in the water here as far as our calculations go. We're going to say we start with 0 and 0 here. However much acetic acid we end up with, that's the same amount of hydroxide we end up with, right? So we can assign the same variable, give it x, then we can set up our Kb expression, except we need to know Kb, right? So how do we get Kb from Ka? I heard two, what was it?
K water. I use K water.
Kb over K water?
K water.
So 1 times 10 to the negative 14 divided by the K that we're given, 1.75 times 10 to the negative 5th. That is going to be equal to x squared over, put this in here, we have 0.5 minus x is our final concentration of acetate. Okay. So, all right. So I came up with a Kb of 5.71 times 10 to the negative 10. And that will be equal to our x squared over 0.5 minus x. Okay. So this would be a situation where we're going to end up with a quadratic, right? And hopefully you guys remember whatever strategy you use to solve quadratics for the solution of the quadratic equation. But however you get there, you should end up with 1.69 times 10 to the negative 5th molar. Okay. And that's going to be equal to our hydroxide ion concentration, right? How do we get pH from that? Remember that the pH plus the pOH equals 14, right? So we can rewrite that to be the pH is going to be equal to 14 minus the pOH, right? So we're going to plug in our hydroxide ion concentration, the negative, the log, 1.69 times 10 to the negative 5th. Good? And I came up with a pH of 9.228. Makes sense? We have a weak-based solution. Okay. All right, second part of the question there. If the solution of acetate was titrated with a 2 molar hydrochloric acid solution, the pH at the equivalence point would be, i.e. is it going to be basic, is it going to be neutral, or is it going to be acidic? It's going to be acidic. Everybody agree? It will be acidic. Keep in mind, anytime we titrate a weak base with a strong acid, what's going to drive the pH at the equivalence point? We're going to be taking our acetate here, we're going to add acid to it, right? And we're going to form what? We're going to make acetic acid, right? So at the equivalence point, we have a weak acid solution. Better be acidic if we have a weak acid, right? We are asked to then determine what is the actual pH at the equivalence point. I'm going to skip that just because I want to get through more problems, because that's basically a Ka problem, right? Which is going to be using the same strategy we did here for Kb, except we're going to look at the dissociation of our acetic acid. Everybody remember how to do that, or you want me to do it?
Keep going.
All right, so let's look at the last problem here. If we add 10 milliliters of our 2 molar HCl, which is well before the equivalent point, what is the final pH going to be? Okay. So we're carrying out some amount of our titration reaction here, and we're going to determine at that point in the titration what the pH is. So our titration reaction, again, is our acetate plus our hydrogen ion, our acid, going to acetic acid, right? Okay. I'm going to express this in moles, which were given in the first part of our problem. We're told that we have 0.250 moles of acetate. Right? We're adding 10 milliliters of 2 molar HCl. So if we multiply our 2 molar solution by 0.0100 liters, we're going to end up with 0.0200 moles of acid added, right? And we're saying we start with 0 of our acetic acid. Well, we can see clearly that the hydrochloric acid that we added is going to be the limiting reactant, so that's going to go to 0. We're going to subtract that, so we end up with 0.230 moles, and we're going to end up with 0.02 moles of our acetic acid, right? All right, how are we going to come up with pH once we know where we're at in our titration? Henderson-Hasselbalch, right? Okay. So pH, what is the Henderson-Hasselbalch equation? pH is equal to pKa. No, we're going to have, well, A minus for base over HA for acid, right? Okay. So pKa, we're going to take negative log of our Ka, which is given. We're going to come up with 4.757 plus the log. We can leave things in moles because it's divided by the same volume if we were to put this in molarity, right? So we're going to take 0.230 moles divided by 0.0200 moles. Right? Always base over acid with the Henderson-Hasselbalch equation. And we end up with a pH of 5.818. And again, keep in mind that we can do those quick checks. We know that we shouldn't be too far from our 4.7 pK value. We know that we have more base than we have acid, therefore the pH had better be something more basic or larger than our pK, right? Okay. Any questions there before we move on? Get into a little bit of electrochemistry here. All right, so I give you a galvanic cell here, and we're going to determine potential under certain conditions. All right, so we have a galvanic cell. We're given a couple of half reactions. We're giving standard reduction potential for the reduction reactions, and we're given a concentration of 0.072 for the cadmium nitrate and 0.115 molar for the silver nitrate. Okay. Let's come up with a net cell reaction. Okay. We can do that by taking our oxidation and combining it with the reduction, right? Okay? So we have, for our oxidation, we're taking cadmium. We're going to cadmium 2 plus our 2 electrons, right? Now, if you look at the way the cathode reaction is written there in the half reaction, it's already taken into account balancing the electrons. But really, what's going on at the cathode is that we're taking silver plus ions, combining with an electron to get solid silver. Okay? But in order to add these two reactions together to get a balanced redox reaction, our net cell reaction, we have to multiply that second one by 2, right? So we're going to end up with cadmium plus 2 silver ions going to cadmium 2 plus 2 silver, right? So let's write the Nernst equation to solve for the potential for our balanced net cell reaction. Okay? So we're after our cell potential. That's going to be equal to what? What's that going to be equal to? We got to take into account our standard reduction potentials, right? So we're going to take the standard reduction potential for the cathode, right, 0.77, or excuse me, 799. We're going to subtract the standard reduction potential for anode, so minus negative 0.402. Okay. We're going to assume that we're at 25 degrees Celsius. So we're going to have then minus 0.05916 divided by the number of electrons involved. Okay, so we're looking at the balanced reaction now, and there's 2 electrons involved in that redox reaction, right? Log of the reaction quotient, okay? So we're going to have the concentration of cadmium ion over the concentration of silver ion squared, right? Okay. So we'll have 0.072 divided by 0.115 squared. Okay. Does that ring a bell? Okay.
And then minus the cathode, right?
So we have the cathode minus the anode, right? Okay. We should come up with a potential of 1.1 volts. Certainly I would say something like the Henderson-Hasselbalch equation, Ka, Kb, the Nernst equation are things that you should know going into the exam. And those are the type of equations that are very commonly used. Okay? Any questions there?
Do they give us anything? I know that they probably have to give us a
Yeah, so they would give you things like standard reduction potentials, or if you need a constant. You know, they're not going to expect you to remember Planck's constant and Boltzmann's constant, things like that. All right. Goes back to early discussion of the semester. We have a 50 milliliter Class A burette, and we're essentially calibrating it. So we're looking at the measured volume, so what we measure off of the burette itself, versus what we actually dispense. Okay? So this is the measured volume that you would get off the burette. We could then take the dispensed volume, determine its mass, take the density at whatever temperature we're operating at, in order to get back to the actual volume dispensed. Okay? So this is what we read off of our tool, our burette, and this is what we're actually getting. Okay? I want to know what kind of error do we have? How can we describe this? How might we tackle this? Remember, we at the beginning of the semester, we talked about systematic error, we talked about random error.
It's almost systematic, just because with the lower milliliters over here, it's lower milliliters over here, so I don't, of course.
Okay, so when you say the lower volumes over here equal lower volumes over there, are you saying, well, we have 10, and 10 is the 10 is always lower than the 30, the 10 is always lower than 30, or?
Yeah.
Okay, well that's
always
that better be the case, otherwise we get a really screwed up urette.
Yeah.
Right? So what we've done is we said, okay, what we're doing is we're determining what's the error at a small volume dispense, what's the error at a moderate volume dispense, what is the error when we dispense almost the whole volume of the urette. Okay? What else might we look at? What is the difference? Right? We might be interested in saying, okay, well, we dispensed right around 10 mils. That was our goal. We got pretty darn close to that. And every time we dispensed 10 mils, we actually got something less than that. We tried to dispense about 30 mils. Got pretty darn close to that, at least as far as our measurement goes. But we always ended up with actually less than 30 mils. Okay? We dispensed right around 50 mils here, but we always got less than we measured on. Okay? So we might be interested in determining what is the actual error that we have. Now there's an extra 6 mig there, but that's just, we can round up if we want. Okay? But we do have what type of error? It is systematic. We are always ending up with a measured value that's greater than the actual value. Okay? What else can we say there, looking at the differences? It's not constant. So we have reasonably similar values for our air when we try to dispense 10 milliliters. We have a larger amount of air, relatively similar, when we dispense a moderate amount. We have even more air when we dispense the whole 50 mils. So we actually have a systematic error that is proportional to the volume dispensed, right? Or we might even say that it's volume dependent error. Okay. Any questions there? Moving right along then. All right. Got a titration question for us. We have a 25 milliliter sample of lanthanum 3+. We treat it, we react it with sodium oxalate. The oxalate reacts with the lanthanum, so that we end up with that species given there. We wash it, in other words, we're getting rid of any excess oxalate that might be present. We then take our lanthanum oxalate and we dissolve it in acid. Okay, so now we have the lanthanum and the oxalate that was together, now in ionic, or as ions in our solution. We then titrate that with 12.34 milliliters of a 0.004321 molar potassium manganate solution. Okay? This is the reaction down here. We're going to get a reaction between the oxalate and the permanganate. When the permanganate has a nice purple color. So as soon as there is the slightest amount of excess permanganate, that marks an endpoint. And we know that we have reacted all of our oxalate, and we see this purple color. Okay? I want to know what is the concentration of lanthanum in our original solution. Kind of a back titration type problem. We're not measuring the lanthanum directly. We're measuring the oxalate that reacted with the lanthanum. We know how much oxalate came from the lanthanum oxalate, right? Is that Make sense?
From the moles of the manganate or permanganate, and then ratio.
Okay, so we're going to go from moles of permanganate to moles of what?
Oxalate.
Get our moles of oxalate, and then from our moles of oxalate to the lanthanum. Exactly. We can set this all up in a single dimensional analysis. Okay, so we'll take the volume of our titration, convert that to liters, so we'll have 0.01234 liters. That is our permanganate solution. We know the concentration of our permanganate solution, so we can get the moles of permanganate. Your concentration is 0.00431 molar, or moles per liter. Okay. If we were to stop there, we'd have our moles of permanganate. We can look at our balanced titration reaction to relate permanganate to oxalate. So 2 moles, 904 minus, right? Reacts with 5 moles of our oxalate. All right, so now we would be in moles of oxalate, right? We can look at our ionic compound here to get the ratio for the moles of oxalate to lanthanum, right? There's 3 moles of oxalate. 2 moles of lanthanum, 3 plus, right? Okay, we stop there. We need moles of lanthanum, but we need to go to molarity. We do know the volume of our original solution of lanthanum. It was 25 mils, so we can divide by 0.02500 liters to get back to molarity, right? I come up with 0.003555 molar lanthanum 3 plus. Any questions there? I doubt we're going to get through everything. Probably try to get through 2 more here and kind of skip around to get to a couple of other subjects that we haven't hit on yet. All right, so we carry out replicate analyses of carbohydrates. We're looking at the amount of carbohydrates in a glycoprotein, and we find that we have 12.6, 11.9, 13.0, 12.7, and 12.5 grams of carbohydrate per 100 grams of protein in our 5 replicate analyses. I want us to find the confidence interval at the 50th and 95th percent confidence intervals for the carbohydrate content. Okay. So, first thing is to remember how we determine a confidence interval. What is a confidence interval? You guys remember what it is? It'd be a good place to start.
No confidence.
Okay, exactly. So we said that we would say that the true mean, okay, is going to be equal to our sample mean, our experimental mean, from our 5 samples. We can't determine the true mean of a sample from such a small sample set. We need a large number of samples in order to establish what the true mean is, right? Okay. But we're going to say that it is within a certain range of our experimental mean, okay? And that range is going to be T times the standard deviation of our replicate analyses divided by the square root of n. Okay? So really, this is what we're using to establish the bounds of our confidence interval. So we're going to say that, well, it's plus or minus some value from our experimental mean. Okay? Well, so we're going to need our experimental mean. Happens to be 12.5. And that's going to be the same. We talked about the 50th and 95th percent confidence interval. Where does that come into play? Our t-value, right? That's going to, our t-value. So we're going to need some t-values. If, obviously, if you need something like a t-value or an f-value from our f-test, then they're going to have to give you some information, okay? So let's do the 50th percent confidence interval first. So we're going to be looking in this column. How many degrees of freedom? Okay, we have 5 measurements, right? Didn't we? Yeah, we got 5 measurements. So it's n minus 1 degrees of freedom. So we're going to use the, what? We're going to use 0.741, right? Okay. We're going to have to determine the standard deviation. Okay. I think most folks know how to get their calculators to do that. Is that correct? Sure? No?
I can never do anything.
I'm sorry, what?
We can use it.
Yes, you can use a calculator. All right. In that case, the standard deviation, I'll just write it, give you the formula here, is going to be the sum, actually we're going to take the square root, no, the sum of the square root of the average minus the individual measurement squared over n minus 1. Right? So we're going to take the difference squared, sum all those up, take the square root over n minus 1. Right? Something doesn't seem right to me.
Yeah, that's right. I mean, you see it usually as x minus the average, but then we use just the difference.
Yeah, because we're squaring it, that's not going to matter. Okay, I'm pretty sure I have that wrong. So it's going to be the sum of those differences divided by n minus 1. We're taking the square root of that whole thing. Okay. Standard deviation for our samples can be 0.4 if we want to carry one insignificant digit through, it happens to 0. Okay? Divided by the square root of n, or square root of 5, right? So at the 50th percent confidence interval, you have 12.5 plus or minus 0.13, and it happens to be in units of grams there. Okay? So if we really wanted to say what is the range of values, we could say that it's going to be, we can subtract this value and come up with 12.4. We could add that value, 12.6. So at the 50th percent confidence interval, we're saying our true mean, our true value is somewhere between these two, right? Okay. Now, let's do this at, so this is at the 50th percent confidence interval. Let's do the same thing at the 95th. The only thing that's going to change is this t-value, right? Everything else stays the same. So we'll have 12.5 plus or minus. I'll come over here, still working with n minus 1 degrees of freedom of 4. We're going to come over and we get 2.776. Everything else is the same. We're going to end up with 12.5 plus or minus 0.49. So we end up with 12.1 to 13.0 grams as our range. Okay. makes sense that if we want to have more confidence, if we want to be more confident that our range includes our true value, we got to throw the net further. We got to make that a wider range, right? Okay. Any questions there? All right, I'm going to skip the next one, next couple, and we'll do a coulometry, or a coulometric titration problem here, and we'll finish up here. All right, so we're carrying out a coulometric titration of sulfuric acid here. We are generating the hydroxide bed. We're going to titrate our sulfuric acid using this device here. You see that we're producing our hydroxide at the cathode. Okay? And so we're given a reaction that is occurring at the cathode to get our hydroxide. Okay? We're told that we're operating at a constant current of 0.0676 amps, and that we have to carry out the titration for 212 seconds. Okay? We don't have a titration reaction here. We should certainly be able to come up with that. We know that we have sulfuric acid in our solution. We're trying to determine its concentration. We're going to do so by adding some hydroxide, right? What do we get when we mix strong acid, strong base? We're going to get some water. Okay? And we're going to get some ions in solution, or soluble salt. In this case, the way we've written it, we're going to end up with some sulfate in solution, right? Good titration reaction? Everybody happy?
Oh,
Is it balanced?
no.
No? Is that better? Okay, gotta make sure we have a balanced titration reaction. We need that stoichiometry. All right. So, we're carrying out this reaction at a constant current for a certain amount of time. How are we going to determine how much titrant we've added? How much hydroxide? We don't know our unknown acid solution, so we had better be able to figure out the amount of hydroxide we used, right? How are we going to get that? There's an equation for it. Okay. Well, do a little dimensional analysis. So we're operating at 0.0676 amps. How else can we express that? Coulombs per second. Okay. We know the seconds. 212 seconds. Okay. Multiply that by our 0.0676 amps, or coulombs per second. Now we're in coulombs. Okay. How do we get from coulombs to maybe moles of electrons? We're going to use the Faraday constant. For every 1 mole of electrons, there's 96,485 coulombs. Okay. Now we have moles of electrons. What can we do with that?
Relate it back to the titration problem, or relate it back to?
Okay, well, we can relate it to something in our titration reaction. What? We can relate it to the hydroxide, because we know what the reaction is that's occurring in our cathode. We're given that in the problem. We see that for every 2 moles of electrons, we get 2 moles of hydroxide, right? Yeah.
So you think they give us Faraday's?
I don't know for a fact. I don't know for a fact that you'll need Faraday's constant. I spent a couple of years since I've looked at the exam, and to be quite honest, I purposely did not look at it right before this because that might bias what I include in a review. So I'm trying to go over everything that we covered in the class to give you a broad review. But I would suspect that Faraday's constant would be just like any other constant, just like Boltzmann, just like Planck's constant. They're not necessarily values that you're expecting to know, just like the t-values. If you need t-values, They're gonna have to give them to you, right? So what I would be most concerned with is knowing how to solve the problems, right? Know what formulas that you're going to use, right? Just like if you have a Henderson-Hasselbalch problem, then you're not gonna have to know what the pKa is, right? They're gonna have to give you some means to get to the pKa or give it to you directly, okay? All right. So, we have what's going on at the cathode. We can say that for every 2 moles of electrons, there's 2 moles of hydroxide being produced. Okay? So now we're to hydroxide. Now we can go to our titration reaction and relate the amount of hydroxide to the sulfuric acid. So we use 2 moles of hydroxide for every 1 mole of sulfuric acid that we consume in our titration reaction. We ultimately are going after a concentration, so we're going to have to divide by the volume of our original sulfuric acid solution, which happens to be 100 mils, or 0.1000 liters. Okay? And I came up with 7.43 times 10 to the negative 4th molar sulfuric acid. Okay. All right. We're going to stop there. We're done with quant, more or less. Get through the final. The final is 8 a.m. Monday. So we'll get it out of the way real quick in the final score. Okay. If you have any specific questions on problems, I'll make a point of taking my textbook home. So if there's something you want to refer to in the textbook, you can. If there's something covered in lecture, shoot me an email, and I will make a point of periodically checking my email over the weekend. Okay?
I got negative 6 though on that.
Negative 5th?
You were negative 6.
Negative what?
I got negative 4 as well.
Oh, because
Alright.
I didn't divide by 1. That's right.
Okay.
Okay, so, please.
All right. Thank you.